Hi, welcome to this video about calculating acceleration. First, I got a question for you. What's a velociraptor? Oh, it's a distance raptor divided by a time raptor. That one is actually good. Yeah. Okay. So to show you kind of what we're talking about here, I've got this little simulation I found where they just sort of take a tiny little rocket that actually has two stages. So booster and sort of a second stage, and then they graph both velocity over time and position over time at the same time. So let's open it. It's on this web page. Open here. Wait for Nerd Island Studios to load. Okay, so here's our rocket. I'm going to hit play, and we're going to watch the graphs. There it goes. So notice it ran out of fuel and exploded for some reason. Let's play it again. Maybe they will actually keep tracing the line this time. They're not, which is aggravating. But anyway, what you saw is, first let's notice a couple things. The velocity changed, right? The velocity changed this whole time, but it also didn't just change, its slope changed, right? The slope of the velocity changed. Notice also the velocity started going down after it ran out of fuel and became negative, right? It became negative. What does negative mean? It means it moves back towards where it started. And that's when it started falling down out of the sky. So you can see it ended down here, way down in the negative territory. How about position? Well, notice that the position graph is actually curved here. It's actually curved here. What does that mean that it's curved? Well, that's because the velocity is not constant. Velocity is not constant, so it's curving the position. This is still linear, but going up. This is curving and going up, right? So that's telling us that the velocity is changing constantly. The position is not changing constantly. It's changing at an increasing rate. That's kind of what the heart of acceleration is all about. So let's go back to looking at what we were looking at, and here is some of that data sort of highlighted, right? So we're looking at these graphs to find acceleration. What is acceleration? So here's just your plain old note that you should have. What is acceleration? Acceleration is any change in velocity. Any change in velocity. Now remember, velocity is change in position over time. And so velocity is not simply moving forwards, right? Velocity is going somewhere. There's a direction involved. So that means that acceleration can be increasing speed, it can be decreasing speed, and it can be change in direction, or it can be some combination of those. And the thing that is most confusing to students is that in everyday life, we think of acceleration as usually you're starting to go faster and faster, right? You hit the gas in your car, you're accelerating. Sure, that is one kind of acceleration, but there are several other kinds of acceleration. So when you're braking in a car, you're also accelerating. Or when you're turning the wheel and changing the direction that the car is driving, you're also accelerating because you're changing the velocity. And so what you can see in these graphs is I just kind of highlighted what came out of that simulation. You can see that where the velocity was going up, the position graph was going up in a curved, nonlinear fashion. And then when the velocity is going down, the position is starting to come back. It's starting to come back towards where it started. So as this velocity goes down, it starts to come back, and then when it gets negative, it's really dropping, right? So the negative part of this is equal to where this is going down, right? Down and back towards where it started. Okay, here's the formula for finding the acceleration of something. Finding the acceleration. If you think about it, it's not really very complicated. It's essentially the same thing as calculating speed. You take your final velocity, so if an object moves, you take the final velocity it had, you subtract the starting velocity or initial velocity, and you divide it by however much time occurred between those changes. And this right here is the same thing, it's just written in math symbols. So A for acceleration is equal to VF, big V, little f means final velocity minus VI, that's initial velocity divided by t for time, right? That's it. So make sure you have this formula and you understand what it means in your code. Okay, the units for acceleration, those are any kind of speed units divided by any kind of time units. So commonly what we would say is meters per second per second. Sounds funny, right? Sounds like I'm repeating myself. Meters per second, because let's say, for example, I was going 3 meters per second at first, and I ended up going 5 meters per second, and it took me 2 seconds to make that change. Well, that would be 2 meters per second in 2 seconds, which is 1 meter per second, which can be abbreviated as meters per second squared, just because you end up multiplying these two s's together. But you might see other ones, for example, kilometers an hour per second, or miles per hour per second. If you're actually sort of measuring your acceleration in your car, you might say, how many miles per hour can this change in 1 second? And then acceleration can be negative, just like velocity you've already learned can be negative. Negative velocity means moving in a negative direction. Acceleration can be negative, and actually in multiple ways. So if an object is moving in the positive direction, so this car right here is moving in the positive direction, which is to the right, and right now it's accelerating in the positive direction, so that's positive. But in this case, and I highlighted the 2 negative acceleration cases, in this case, it's moving in this direction, but it's accelerating in the opposite direction. So this is a case of a car slowing down, right? The car is slowing down, so its acceleration is actually in the opposite direction of its motion. Or it is speeding up in a negative direction, right? So we said that right is positive, so left is negative, and if it's speeding up in that negative direction, its acceleration is going to be negative. Okay, here's an example of how we can do some calculations with this stuff. So I got a Ferrari, of course, obviously, and it has initial velocity of 10 meters per second, and accelerates at a rate of 50 meters per second for 3 seconds. What will its final velocity be? So let's write out our formula. Acceleration is final velocity, so v with an f, minus initial velocity with an I, divided by time. And what do we know? Well, we know the acceleration, says it right there. We know the final velocity, sorry, that's our unknown, right? That's our unknown. We know this to be 10, and we know this to be 3, and we know this to be 50. So let's plug in. 50 meters per second squared is equal to the final velocity minus 10 meters per second divided by 3 seconds. Couple things we can do here, but the easiest one is probably to multiply both sides by that 3 so that we get it out of the way. So multiply by 3 here, 3 here. So that becomes 150 is equal to final velocity minus 10. And since this is seconds, this becomes meters per second. So meters per second. This is also meters per second. And now we need to move this 10 over here by adding it to both sides. So that's 160 meters per second is the final velocity. There you go. That makes sense. Okay, let's try another one. Okay, we've got a car traveling at a speed of 30 meters per second and it encounters an emergency and comes to a complete stop. How much time will it take for the car to stop if it decelerates at -4 meters per second squared? Okay. Interesting, we've got a negative involved here. So again, here's our formula. Acceleration is final velocity minus initial velocity divided by time. And this is -4 meters per second squared. This is our unknown. Our initial is 30, right? Now, what is our final? Right? What is our final? Well, that's what we have to use this for. Comes to a complete stop. So that means the final must be 0, right? This is something that students often struggle with. If it says comes to a stop or starts from a standstill, right, that means 0. So now what we have is -4 meters per second squared is equal to our final velocity, which is 0, minus 30 meters per second, divided by the time. So 0 minus 30 is negative 30. So we really have minus 4 equals minus 30. So we can kind of scratch out this 0 because it doesn't do anything. And then you might remember this trick where we put this over 1 and then we cross multiply. So that means minus 4t, not 40, but 4t equals minus 30. And we have a minus on both sides, which is good because time cannot be negative. Time is a scalar quantity. It can't be negative. So we want it to cancel. We want it to become positive. So t is minus 30 divided by minus 4, which is also known as 7.5, right? 7.5 seconds. 7.5 seconds. So 4 goes into 37 times 28, remainder of 2. 2 over 4 is half. So 7.5 seconds. That's our answer right there. It takes 7.5 seconds to stop. Alright, so that's what I got for you. Those are some examples on how to calculate acceleration problems and understand what acceleration is. A bit tricky because what negative acceleration means is a couple different things. And remember, acceleration happens anytime you change your speed or your direction. Keep that in mind. Alright, see you in the next video.